surface area. How do we get to the formula? So suppose you have a surface like S. And suppose R is the shadow of the region in the plane beneath it. Suppose your surface is defined by the following relation. F of X, Y, and Z is equal to C. If the surface is smooth, it means that the partial derivatives are all continuous and they are not zero on S. So it means that we're working with the gradient. The gradient is continuous and it doesn't vanish. It means that it's not equal to zero. Then we can define and calculate the area as double integral over R. How do we do that? So the very first step is to partition S into smaller regions. Suppose we graph this. Suppose you have your surface. This is your S. Just make it a little bit larger. And the shadow of S on the plane is just R down here. What are we going to do? We're going to take a look at the shadow of S on R, and we're going to divide this guy into smaller pieces and look at the small pieces of S on top of it. Very good. Suppose you take a very small piece, I'm going to make it a little bit larger so for you to see what is going on here. We're going to take this small rectangle and we're going to call it delta A sub K. This is this guy here. So of course, it is some part of your surface which is reflected shadow in the plane. So let us take a look at this up here, and I'm going to use the same exact color. Okay, let me just match this hopefully correctly. Avoid any confusion. Above your delta AK, you're going to have a very small patch of the surface, and let us call this delta S sub K. It is going to be just lies on the surface. This guy is called delta S sub K. This patch is on the surface itself. Let's take one point to have something to work with. Let us call this point T sub K, XK, YK, and ZK. What do we have here? The gradient of the function at this point and a unit vector like P, which is normal to R, are going to be available for S and R. So let P be a unit vector that is normal to R. And of course, at any point, you can define the gradient of the function. So since P is normal to R, this unit vector is going to be normal at this point as well. So take a look at this. Suppose you have your unit vector P at any point. And for your gradient vector, you have the gradient of your function f. We're going to use these vectors and eventually define the area using them. Suppose we introduce two more vectors. Let UK and VK vectors, UK and vectors VK, lie along the edges of delta P sub K, which is parallel to delta AK on the surface. So this is your delta PK. By finding the cross product between these two, you're going to have a vector that is normal to this plane, small plane, delta PK. Note that the cross product between UK and VK is going to be parallel to the gradient of F. Recall that from elementary calculus. The magnitude of the cross product of UK and VK dot P is the area of the parallelogram defining by UK and VK. So what's the meaning of that? It means that delta AK, this area, is nothing but the magnitude of UK cross VK dot P. If you break this down, you're going to have delta AK, which can be written as the magnitude of the cross product between UK and VK, the magnitude of vector P, times the cosine of the angle between UK cross VK and P. Okay, this is the definition of the magnitude of the cross product dot P. You can replace it with any vector that you like. So if we simplify this, this magnitude represents delta pk. The unit vector has a length 1. And this is the same as the cosine of angle between the gradient and P. So it means that we can just simplify this as the area of PKs, which can be written as the magnitude of these areas divided by the cosine of the angle between gradient of f and the unit vector P. Now, if you take the sum of both hand sides and take the limit, it converts into the double integral. The double integral of dA divided by the cosine of the angle between the gradient of f and P. Very good. Now we can present our formula. The area of the surface is equal to the double integral of the magnitude of gradient of f divided by the magnitude of gradient of f dot p dA, and p is a unit vector normal to R. And note that the gradient of f dot p is not 0 on the denominator. Just a quick reminder for you. Let me erase this part of the board so I can write it for you. When you're talking about the gradient of f dot p, this guy can be written as the magnitude of the gradient times the magnitude of p times the cosine. So since you had dA over the cosine, you can replace this by the gradient of f. This is just 1. On the denominator, you end up with the gradient of f dot p, its magnitude. That's how we end up with the formula. Just doing the substitution for cosine down here.